Okay, so for this problem we have a brick sitting on an inclined plane, and what we're going to do is find the maximum angle where the brick will stay on the plane, and then we're going to calculate the coefficient of static friction between the brick and the plane. So Stacy, can you slowly raise the plane for us? So we're at 5 degrees, 10 degrees, 15, 20, 25, and it looks like it slid at about 27 degrees. Thank you, Stacy.
Alright guys, so for this problem we want to find the coefficient of static friction. So what happened is right as the brick slipped, or right before it slipped, whichever way you want to think of it, we had the brick at an angle, and that angle was 27 degrees. Now there's really only two forces acting on the brick. Three forces acting on the brick. One of those is the normal force, and because we're sitting on an inclined plane, that normal force is not a vertical force anymore. It's perpendicular to the inclined plane. So what actually happens is that is 27 degrees from the vertical. And then another force we have acting on our brick is we still have weight, and weight is always straight down. And before the brick slid down the hill, we must have had friction sliding up the hill. And we basically figured out that 27 degrees was when we had reached the maximum amount of friction possible. Because if we go just past that, then the brick slid. So what we're going to do is figure out the coefficient of static friction there. Now, when we're doing this type of problem, instead of having the y-axis straight up and down, and the x-axis straight horizontal, it actually makes life a little easier if you tilt your head, in this case a little bit to the right, and you think of this as your y-axis, and you think of this as your x-axis. And if you do that, you end up leaving, I forgot to label the normal force there, you end up leaving both your normal force and your friction force alone, and the thing you end up splitting up into components is the weight. And so what happens then is your normal force is left alone, your Fs max is left alone, and we split up our weight into components. Because what ends up happening is one component of the weight, the component opposite to the normal force, kind of presses our brick into the plane, into the board. But then there's another component of the weight, the one opposite of our force of static friction, that makes it want to actually slide down the hill. And so when we break that up into components, the horizontal component, or the part parallel to the plane might be the best way to think of it, ends up becoming mg sine of theta. And the part that's opposite of the normal force ends up becoming mg cosine theta. And I'll explain that further in class, but that's something you're just going to want to have straight in your head and memorize, that the part that's parallel to the plane will always be mg sine theta, and the part that is perpendicular to the inclined plane will always be mg cosine theta. So on the next slide we will set up our equations for equilibrium. So I've gone ahead and written our two equations. This is our net force X equation, right? So we have that the force to the right and the force to the left are equal. And then here we have our net force Y equation, because we have shown that our force up and our force down are also equal. So the other important equation, of course, that we're going to need since we're trying to solve for the coefficient of static friction, is the Fs max equals mu s n. And so if we're solving for mu s, then mu s, of course, equals Fs max divided by n. But we said earlier that Fs max is equal to mg sine theta. And we also said earlier that n is equal to mg cosine theta. So this is a really cool thing. We know the value of m, that's a 1.5 kilogram brick, and we could plug that in. And we know that this occurred on Earth, where g is 9.81 or 9.8 or 10, whatever we wanted to say. But here's the really neat thing. Even if we didn't know the mass of the brick, the masses cancel out, so we don't even need them to solve this problem. And even though we know the value of G in the classroom, we could do the same experiment on the moon or Mars. G cancels out, so we would always get the same value there as well. And then if you know your trig identities, you know that sine of theta divided by cosine of theta is the same thing as the tangent of theta. So for this particular problem, it turns out that the coefficient of static friction actually just equals about the tangent of 27 degrees, which is 0.51, which is pretty similar to what we got for the brick on the table in the examples we looked at yesterday. So remember, I've been talking to you guys about how I always want you to rearrange equations before you start solving, and this is when it becomes very important. It becomes real important when we're solving system of equations, because if I hadn't given you the mass of that brick and you didn't rearrange first, if you tried to solve it in parts, you wouldn't have figured out that the mass cancels out and you can solve the problem without it. So make sure you're following your problem solving steps in the order I've been telling you to, I've been doing in the examples.